We are in session 4A. If you were planning to be in session 4B, it's on the 3rd floor. You can take elevator from the registration desk, next to the registration desk. And then there are signs for the room, Providence Ballroom it's called. But we are here in session 4A on planning and interconnection of large loads. And it's my pleasure to introduce Sam Morris, Manager of Load Forecasting and Analysis in ERCOT, and the incoming chair of large load task force that we are kicking off at ESIG. And Sam will talk more about that.
Thanks, Julia. All right, so we'll start out. My name is Sam Morris. I'm the Manager of Load Forecasting and Analysis at ERCOT. And who remembers CFLs, right? Okay. Remember, it was all of a sudden, boom, killed all of our forecast, right? Just went away. Now we have a new paradigm, large loads. And these large loads, this time last year, we were talking about, oh yeah, you know, you got a few here, a few there, not a big deal. And then all of a sudden it was, no, here comes the wave. So kind of put it in ERCOT perspective, this is what the wave looks like. Going from 86 gigawatts to 148 gigawatts by 2030. So here we kind of break it down a little bit, but our crypto load, we also have hydrogen and industrial, right? So the hydrogen has the industrial to support it and things of that nature. But then this big one in the middle, the data centers. Ooh, the scary one, right? So everybody wants to talk about it. ESIG has said, okay, fine. We're going to start a task force for this. So basically what we're looking to accomplish here, and I think there's actually a couple that we could actually add to this too, but it all starts at the load forecasting level, right? So how do we forecast these guys? But I think before that, we even have to think about how do we ask for this information, right? When we're talking to transmission owners or distributions, what are the questions that we need to ask? Then we follow that through to the interconnection process and the performance requirements for these loads. I mean, some of these loads are measured in gigawatts, you know, not where we've normally been. Then we have to think about our modeling requirements, transmission planning, how all of this fits together in our markets. What is the resource adequacy needed for this? And then getting into the regulatory aspects of it. So that's all things that we want to start talking about. We want to open up the conversation, and that is why Julia has established this large load interconnection task force, and we look forward to having you guys. So now I'm going to turn it over to Julieta, and she's going to start us off.
Let's see. Is the mic? I think that we have to wait for them. Oh, no, it is very low. We don't have to wait. Let's see. Can you guys hear me now? Is that loud enough? Perfect. Very good. So I'm Julieta Giraldez. I'm a Director of Integrated Grid Planning at Electric Power Engineers. We're an engineering consulting firm. And I am here to talk about a little bit of what I've heard as chair of the long-term load forecasting task force that I've been leading for ESIG over the last year. And what I'm going to focus on is large loads. Sort of, you know, we've been hearing them on the headline. What are we talking about? Sam introduced it a little bit here. Data centers, we have them there in the tens to hundreds of megawatts. But really the last EPRI survey, right, was most of them are between 500 and 1 gigawatt now. And I wonder what numbers we're going to see at the next ESIG event next year. Cryptocurrency, electrification, and then also commercial and industrial manufacturing loads. And the one that is sort of now causing the most conversation and that we're going to talk about, although we're going to also talk about a little bit about the process for smaller ones at the distribution level, but it's really these data centers, the big sort of I think unique thing about them is their size, right? They are truly beating any expectation there. So I'm going to talk a little bit about from the forecasting side of spot loads or known loads, which is a term that distribution uses for those sort of new customer interconnection requests that are larger than residential customers and mostly large loads. So the reality is that in terms of forecasting, there is no formal forecasting model for this type of load. Nobody is really using any sort of science-based modeling approach for them. They are very large, as I was saying, and their unique thing and why they're so hard to deal with is they're really, heterogeneous and binary. I mean, when you produce a forecast, or you get it right or you get it wrong, now at the scale of gigawatt, it's not like PV adoption or EV adoption. You might get it a little bit wrong, but directionally in an area, you know sort of what's coming versus in another one. And then really to do any formal modeling on them, land-based or anything, you need to understand the drivers. And the drivers are changing constantly, even on these large data center loads. So there was one utility that was sharing that as soon as they sort of understood drivers of where customers were locating these things, like distance to fiber optics, cost of land, then the driver changed. For example, the AI-driven data centers don't care anymore about fast internet connections to do AI. So we're really sort of playing catch up constantly, and we're not able to do formal modeling. So the data really comes from the data obtained by the utilities and the ISOs directly from the customers. And there are some methods for sort of trying to do a little bit of trending or derating the data you have for future years. I put there the link to EPRI's recent report that talks a little bit about some practices there. But again, nothing really formal. And then there's no standardization, as Sam was saying, in the way we model, consider, or even interconnect what data we're collecting to do the modeling for interconnection of forecasting. There's also I've heard it quite a bit this come up in the task force, the concern of what shows up at the meter versus the requested power of large loads. So discrepancy with maybe at the meter, ends up showing 30% of the load that you really originally planned for, and it's not going to get arrive to rated power. And then, so quite a bit, the concern of speculation and how are we really sort of modeling these things with the data that we're collecting. A new type of customer that has also arise now is land developers. They only acquire the land and they build the substation, and they don't even have the customer or the load yet. And so imagine, from the speculation side of things, how do we deal with that? Project development timelines are speeding up. So we heard in the task force sharing, a connection of a 1 gigawatt ramping up to full capacity in less than 12 months, which totally contradicts, the previous bullet that I put there. But just this is the type of information, confusing information being shared and different experiences being shared by the entities. And then we don't really then know also when we're doing forecasting how to reconcile any potential economic load growth, or even when we're doing EV forecasting with this sort of bottom-up data that we're also using and sometimes incorporating in the forecasts. And then, again, very little confidence in, this was also reported by the EPRI survey. We are getting this data, we're using it now for the first time, in 2024, sort of more formally in the forecasts, but there's very, very little confidence in that data that we're using. And to close, I was just gonna say that the other big thing we've heard when you go to any data center or large load sort of conversation is we need collaboration and we need coordination. Now, what that means, how do we actually put that into action? is, I think, the big question. And I was just going to take a second to see if we have any data center developer, customer of large loads in the room. Speaks to itself. These people are very busy building. We have one. Great. We're very busy, building this thing, this load that's coming. And it is really hard to find that time to put this collaboration and coordination into action, but it is highly needed. So with that, I'm going to pass it to my colleague, Ahmed, who's going to also talk about planning and reliability and operational, in case we didn't scare you enough.
Thanks, Julieta. Okay, so I'm looking at the timer, so I'm going to try to make this as informative and brief at the same time as possible. So just for a little bit of background on myself, I spent a good part of my career in operations and then the rest of it mostly in planning. And so whenever I'm planning, I'm always thinking about operations. And our current standards generally for planning have been established based on centralized generation, predictable loads. And with that, that's how we continue to plan today. But we've really entered a time when we're uncertain on the load side. We're a little bit better now in forecasting on the generation side, but for a while, it took us a good time to get there and calibrate our models. So I'm going to talk a little bit about some of the studies we're doing today, talk about some that we should start considering to do and other considerations as well. So steady state studies, everyone knows about these. I think a couple of things to highlight here is participation models can impact what you're going to study. So if you have a large load that's going to be firm, you're probably going to study them at their full capacity. If you have large loads that are willing to be controllable, there is a little bit more flexibility in getting them connected, maybe at a lower level of firm load and letting them take on whatever's available in the grid at any given time. And so with that, that kind of enters into your steady state assessments when you're looking at thermals and voltage. We're looking at short circuit as well, largely for the interconnection stations. Generally, the UPS should not be connecting to the grid. There has been some evidence to the contrary, though, where there is some apparent paralleling of the data center systems with the actual grid. And so this is something for all of us to monitor. I think there's going to be some papers coming out on this in the near term. Transient stability, for the most part, angular stability, transient voltage stability, and frequency deviations, we're really looking here at the loss of the load, or in some cases, the reconnection of the load without actually clearing it with the ISO ahead of time or the utility. So these are situations where you want to look at if the load was to fully reconnect or if the load was to disconnect, what could be the angular stability issues, what could be the voltage, the transient voltage issues that you see, as well as any frequency changes. So these are the baselines that we're all really used to. So I do want to touch on voltage ride-through, and I'm sitting beside a colleague from Texas, where at ERCOT I think has really been pushing this as far as possible. I think recently at one of the large flexible load task forces, there was a moment of pause where I think the developers and the team got as far as they could without any help. And I really applaud kind of the ERCOT team for getting things that far. There are a lot of concerns around voltage ride-through. I think we had an example in the PJM territory recently where for an out of zone fault, 1,500 megawatts of load tripped off out of zone on its own. And when you relate this back to some of the standards they're designing to, there's a curve called the ITIC curve, which really kind of dictates the behavior that you expect to see from large load, IT-based large loads. And this curve, it's the middle one on the screen. If you can see that after one cycle, if the voltage is below 0.7 per unit, you can expect the loads to disappear. That means they could actually go on to backup supply, or they could actually just disconnect. And in that case, let's talk about the disconnection being a problem to start. So you're running and thinking, going back to the operational time frame, you're sitting in your control room chair, your real-time contingency analysis is running, you feel really confident about where you are. But you don't really know where you are because some of these loads might be tripping off when you're not expecting them to be. So how much faith do you now have in your real-time contingency analysis? Now we step this back as well so the loads disconnect for an out-of-zone fault, but they're really eager to reconnect. In some cases, you might find them reconnecting without calling in the control centers. which could also be problematic. So there are some things that the voltage ride-through can lead to causing some challenges with regards to. When we jump into subsynchronous studies, generally ferroresonance, large transformer, high voltage network, you can start running into instances of ferroresonance. So you can think of having two lines in parallel. You're loading up a new transformer on one of those lines, capacitively coupled with the one next door. Now you have a recipe for ferroresonance. So some things to start to consider studying when looking at connections for large loads. Resonance more so will be when you're reconfiguring the system, and controller action is really important. And we'll talk about variability in a moment, but for a lot of these data centers, we should be considering when you're looking at reactive compensation, dynamic rather than static. And I'll get into that, but maybe I'll tease it out a bit now, is if you look at the profiles for them, they can be quite variable throughout the day. And so if you have static devices and you're switching them in 3, 4, 5, 10 times a day, that's going to lead to the end of life quite prematurely. So you're going to end up potentially having more SVCs, STATCOMs on the system and needing to assess their interactions together. And a theme I think we've all been hearing about now has been co-location of projects and how you handle those. So I've got a diagram here from ERCOT from July, which is showing that the 1,000 megawatts of co-location was approved in July, and there's expected to be quite a bit more coming through in the near term. I'm sure everyone's heard about the 3 Mile Island deal that's potentially going through to turn the nuclear plant back on to support there's a Microsoft data center fleet in that space. So definitely this is going to be a theme in the future on how these loads interconnect. And the question for us is going to be, well, how do you model a co-located project? Do they have a single point of failure, or is the load still going to be decoupled from the generator? And could you potentially have one or the other on their own? So how is that going to be modeled? How do you handle them from a queue perspective in areas where there is a queue? So yeah, certainly things to consider in that space. And there's been also quite a bit of discussion around costs and risks. And I think this is very important to all the utility folks in the room. I've seen, I guess, a couple of models recently where the utilities are looking to de-risk any investments, and rightfully so, they're making in the data centers, because there is some uncertainty in the future of the data centers from their perspective. So you're making a 10, 20-year decision on investment in transmission, but you're bearing all the risk in the current mindset. So, AEP has been trying to get a custom rate set. Duke has put forth a take or pay model. So if this is your profile that you're asking for, we're going to build to that profile. And whether you consume or not, you're still going to pay for the profile that you put forth to us. So those have been a couple of things to see on the costs and risk perspective. And so now we'll jump into ops and markets. I think a key question to ask, and there's probably a set of questions going back to Sam's point, what are we going to be asking up front for these? Talking about dispatchability, and one thing we've been, depending on the hyperscaler that you speak to, what prices are they going to respond to? What signals are they going to respond to when routing compute load? So there is some thought that, load is going to be constant, but from what we've seen in some of the conversations that we've been having, there's going to be drivers that dictate where the hyperscalers route their load. Those could be price in a particular jurisdiction. Those could be prices relative to other jurisdictions. And it could also be the marginal fuel in any current jurisdiction. So for example, if, ERCOT is marginal fuel is gas and, PJM is solar, maybe you route to PJM even if the price is a little bit higher. So there's going to be some thought process on that and optimization that's developed potentially by these hyperscalers to achieve the outcome that they're trying to drive towards. And so, going back to that point, how do you forecast this? How do you forecast intermarket relativities and setting up your own utility for success on any given day through the day ahead market or any balancing mechanisms? So something that also, we need to think about how we're going to handle that. Talking about load variability. So these are kind of 5 themes I think I'd talk a little bit about. I have a minute left, so I'm going to try to get through this quickly. So we expect ramping to be something that happens on a regular basis, in particular when considering these intermarket dependencies for where they're going to consume. So if you're talking about that variability, there's likely going to be a need, like I said earlier, to consider a dynamic reactive compensation. Flicker is something as well that I think has been discussed in the industry. And, relating that down to forced oscillations. Large learning models can potentially have a spiking nature to their consumption. And so the read and write have different load patterns with them. And if it starts to happen on a regular cadence, every 3 seconds, every 4 seconds, and if you're Eastern interconnection, 0.25 mode is scary. 25 hertz mode is scary. You start to consider the impacts of having these collectively work towards a potential forced oscillation on the system. And we talked about variability earlier as well. Frequency regulation becomes important. So I think there was a stat by ERCOT that was published at the NERC large load initial meeting that we had about a month ago. And their AGC is being used up today just by the data centers. And they haven't ramped up fully yet. Like they're just getting started. So if you think of the projections that Sam shared, going from where we are today to 150, imagine that variability and how much regulation you're going to need to procure to keep the system balanced. And are there any energy marketers in the room or former energy marketers in the room? We have Joe. Okay. So virtual transactions have been introduced into most of the markets across the nation, and they're meant to be ways of bridging the gap between real time and day ahead. Now you start to think about, okay, if the utilities themselves don't revolutionize how load is forecast within your jurisdiction, somebody else will do it for you, and they will find ways to make profit off of it. So for example, if we don't start to look at load forecasting more holistically or putting bounds on what load patterns are permissible by these loads, somebody else will put together an algorithm that can guess what tomorrow is going to look like, and they can make profit off kind of bridging those issues. And another thing I think that was mentioned in ERCOT was during a peak day, some of the data centers didn't turn off as expected. And so they had conversations with them, and it turns out they were just trying to meet their capability to provide operating reserve to the system. So they came on to be able to turn off. And so that ends up being a little bit counterintuitive from a market design perspective. So as we introduce these things, we need to start thinking about what market design changes that need to happen to really facilitate the system integrating them holistically. So key takeaways just really quickly: operations, thought process in the planning timeframe ends up being critical to ensuring that we're looking at the right things during the planning timeframe. And that's all I have. Pass to Pooja.
Hey, good afternoon. My name is Pengwei from ERCOT. The previous speakers already set a good stage for what I'm going to talking about. So we already know what is the challenges we are dealing today, but I have to say those challenges will be only compounded over the next few years, even for the next 10 years. So while we are working on all those technical requirements for the interconnection of the large load, so make sure they can be collected our grid. But the one thing we have to think about is our grid today ready? How can we accommodate this large amount of load to our system? So for those not familiar with what we are doing, what ERCOT is about. So basically ERCOT, it is an independent system operator for the tax grid. So we operate those transmission lines and networks to serve 90% of the load demand in the state of Texas. Our peak load is about 85 gigawatt, and also we are electric island, so we do not have any synchronous AC lines connecting to east interconnection or west interconnections. It means we have used all the resource within Texas to serve the demand. So before I talk about those large load growth, so in the past, we have seen the challenges already with this tremendous growth of this renewables, solar, wind storage. So you can see within just 5 years, from the 2020 to 2025, our installed capacity of the solar increased from only 6,000 megawatt to next year 50,000 megawatt. The wind, we see about a 10,000 megawatt increase within the 5 years. But solar, so besides solar, storage is also taking off. So back in 2020, we only have 200 to 300 megawatt of the solar storage right now is a big part of our resource mix right now. At the same time, we see those retirement of the thermal generations for about the 7,000 megawatt for those coal and natural gas generations. So this causes two challenges in the dramatic shift in both fuel types and the type of generations available to serve the Texas grid. So on top of this, and this is another challenge we have to deal with, which it is a large load growth. So in the past, our load growth is relatively steady and 1% or 2% year to year growth over the past. So, but right now we just moved to the new paradigm. So this graph shows the actual or projected large load growth for the year 2022 to year 2008. So these large loads could include the data center, triple load, hydrogen, industry load. If those megawatt within this graph materialized for the future, the question is, do we add those generation resources quickly enough to serve this demand? So even you see this graph is a color mapped, so it shows a different bucket for those tracking purpose. So the blue part shows the approved energies. This part is already in operation. And also we, on top of this, we see the green bar, those the planning study approved. This means ERCOT has approved the required interconnection study. So these are some uncertainties about the purple bar and the orange bar. But regarding these uncertainties, you still see the dramatic growth for the large load and also the high interest for those large load to be connected to the ERCOT system. So we have to have this long-term view about the future challenges for the next 10 or 20 years. Make sure our grid is ready and we can reliably and economically interconnect those large amount of the large load. Basically, we have created those study process, which is called the long-term system assessment process. It is a process we use to evaluate potential need of ERCOT grid for the next 10 and 15 years. It is a scenario guided study. Basically, we start with this scenario development and think about how the future will look like, and then do this generation expansion analysis and investigate those future resource mix, and then put it into a load model to understand those efficiency for the transmission network, adequacy of the transmission network, make sure we build those economic transmission network to serve all the demand. For this year, 2024 LTSA study, so we look at the baseline, which is the current trend. And besides this, also we look at those other two scenarios. Both of them consider those significant amount of the load growth and for the ERCOT region. So for the current trend, basically we look at the trajectory of all loading, the factors, and the economic trend, the fuel price. And the two key assumptions made for those current trend, first one is we cooperize between those transmission expansion and this capacity expansion. So it is like a chicken or egg problem. So we have seen our West Panhandle region are the renewable rich area. So we see the build out of this high capacity in this remote area, but it caused some further conditions to transfer the power from the west to east east is where our load pockets are. So if we lack of this capacity, so these generators, renewables, wind and solar could be moved to this coastal or this north central close to the pocket for those load centers. Also, the second assumption we made is for the political purpose, we do not assume any impact of the EPA rules, and otherwise it will restrict those build out those gas units and even limit the annual capacity factor for those cities. But specifically for those second scenario, we consider those large load adoption. So basically we consider the future. For example, if we have all this the load growth materialized, how this could impact our grid need. And the third scenario is a more restrictive scenario. So we consider both this large load growth and environmental regulation together because there are certain ongoing discussion right now at this federal policy. So it could be definitely have some significant impact on what resources will be built and what is the economic for those the new resources come to ERCOT. So we use this different scenario to help us not only to understand the uncertainties we plan for the year out, but also understand that those is the delta, the incremental impact because of the large load growth. So it's very hard to forecast the actual load trajectory because it's new and also because we do not have very good model to forecast this growth. So last year, ERCOT created a new process. Basically, we think collaboration is the key here. So we engaged with the TSPs, transmission service providers, because they have the first-hand knowledge about how much load can be collected to their grid. So we reached out to them and asked them to provide a list of this load seeking interconnection, but they have not been signed interconnection agreement. Because if any load sign this interconnection agreement, they will be factored in our forecast. So our forecast model will automatically capture that part. But this load, they are in the very stage of this interconnection process, but they haven't signed in the creation agreement, but certainly I think they will be collected within the next 10 or 15 years. So based on this survey, in total, TSP project a total about 7 GW of the large load growth within the Texas footprint. Among this 70 GW, about 4,000 MW can be price responsive. This means if grid is tight, price is high. So this node can respond to the high price and got curtailed. And for the remaining part, it's about the 66 GW. This node, they are flat mode. They are firm mode and they need a 24-hour, 7 days, the power supply, make sure keep this running. So this is a trajectory and we put it in our models. So you can see, basically you can compare between those two scenarios and also current trend. So definitely it will be over 50% the increase compared to the current trend. So you can know what is the magnitude of the impact you expect to see. So this is really an incredible phenomenon in terms of both magnitude and also timing. Because remember, those large loads, they want to be collected to the grid as soon as possible. So here is a quick summary for the key assumptions going to the model, and especially for the high load growth and environmental regulation. Also, we want to study those extreme weather impact because 2011 is a very phenomenal year for us. We have very hot summer and what heat and also we have this winter slaps. And particularly for those environmental regulation rule, so we require all those new combined cycle units to have the carbon capture storage, CCS, to meet those regulation requirement. And for those existing combined cycle units, if they are greater than 300 megawatt per unit, so the annual capacity that needed to be limited to 50%. And for the city's capacity factor, it has to be limited to below the 20%. And across all these scenarios, you see over 10,000 megawatt of the coal will be retired, and some will be earlier before the 2032, some will be before this 2039. So basically, we see the load growth and also retirement of this coal. Definitely, this is a cap we need to fill. I think the question is, how can we see those the future? So we run those economic analyses. So at ERCOT is different from the other region. We do not have any carbon-driven policy goals. So basically, developers see those market opportunity and come to ERCOT and invest on those new resources. So our model is purely economic driven. So here is those new capital cost. We put a model, and we put for both those 2-hour batteries, 4-hour batteries, and 8-hour batteries to see how much this different energy duration battery will be built out. And also we consider those smarter nuclear reactor and also these traditional nuclear units in our study. So here is the study result, and basically this graph shows a breakdown of this new resources per field type and by the 2039. So for the current trend, basically we need those new resources from all the field types: storage, combined cycle units, combustion turbine units, solar, and wind. But if we move to those high load growth scenario, so you see the big spike for those combined cycle units, and this is solar. So basically, solar will be running during the daytime and provide those power. And once the sun is coming down, and so those combined turbine units will be running and serve the load during the midnight. And for those, the last scenario, high load growth and environmental regulation, and you see about 8 gigawatt of this battery will be needed to serve this large amount of load. And for wind, because right now we already have this over this 40 gigawatt of this wind in operation, so you do not see much wind capacity to be built out for the future. But in total, we could need this and 3 times, even 4 times of the new resource capacity for those high load growth scenario compared to the current trend. So it is phenomenal and tremendous growth, because even we add those 70 gigawatt of this large load growth, but you need those base load units, those peaking units, batteries, to make sure you can maintain this balancing responsibility across all these time scales. So this is the reason why the additional generation capacity you need is much, much higher than the amount of large load growth. So if you put into those in the dollars amount, so basically for those 2 scenarios, when we expect those high load growth, so on the average, we need at about 20 gigawatt of new resources per year for the next 15 years. And in terms of investment cost, it's about range from the $16 billion per year to $24 billion per year. So this is only the investment required to basically serve those large load. This does not include any additional infrastructure investment for these transmission lines. It's only the how much we need to invest for those additional new generation resources. So if we look at the transmission side, basically ERCOT is already experienced high congestions, and because we have this solar wind in this West Panhandle region, and so you see this situation can get much worse in this 2034 and 2039. So the congestion cost will be $2 billion and $3 billion. For this scenario, we haven't incorporated the large load into the model because it will cause the congestion everywhere. So it definitely need to build these transmission lines to resolve the reliability problems and also resolve those heavy congestions for those future years. Because remember, for those high load growth, we could add over 100 gigawatts of new solar. Most of the solar will be located in this remote area, far from the load pocket. So this is the challenge we have to consider. So quick takeaways, and we know if we have this all this megawatt in our planning queue materialized, so it will amplify the challenges we are dealing today. And we are thinking not about this resource adequacy, but also the stability, the flexible resource need. Also, those need to be considered in the here together. So make sure we have the reliable and efficient grid to serve all this load demand. Because once this large load come to ERCOT grid, it will impact everyone, TSPs, generators, and also those customers already connected to the ERCOT grid today. I think this is all I have. Thank you.
Hey everyone, good afternoon. I'm Pooja Shah. I currently am Chief of Staff to Vice President of Grid Transformation at Georgia Power. And my colleague and I are going to talk to you about what we are currently experiencing on the Southern Company system. So I'm going to give a brief overview of what Georgia has been through in the last year and a half. So just think about the magnitude of just the load that we have seen in a very short amount of time. And then Harish is going to talk more about the stability studies and topics that he has been researching as well. So a little bit about Southern Company. It is a vertically integrated, well, subsidiaries are vertically integrated. We are a regulated electric and gas company. And at least our southeastern footprint is Georgia, Alabama, and Mississippi. So focus today will be on Georgia. So I want to paint a little picture of our last regular cycle IRP, Integrated Resource Plan, and what we had to file in 2023 as an update to that IRP. So what I want you to focus on the chart is just the load growth from new business. This is basically all the new business, whether that's commercial or industrial, that's coming our way. This is in addition to the base load growth. In 2022, after we got our IRP, regular cycle IRP approved in July, we saw at the end of that year about 2,200 megawatts of load just from new business. Majority of the new business, data centers. That trend continued in 2023. We started to see more and more, while the numbers of megawatts are different for 22 and 23 on this chart, the volume of jobs that we were seeing, the volume of new requests, new business were similar. So what did we do about it? We have a very constructive framework with our PSC in Georgia. And we are allowed the flexibility to file for an update to our IRP. So in October of 2023, we filed for an update. And basically, from the time that the 22 IRP was won and we filed in October of 23, 3,600 megawatts of customer choice load, we won that. So what does that mean? Georgia is one of the states where the customers have a choice. And when we say we won those choices, that means we signed with those customers. We signed 3,600 megawatts just within a year of customers. We had to go to our PSC and ask for more resources and upgrades to our system so that we can accommodate more. The typical range of customer, the data center, we have seen up to 1,500 megawatts on one campus of a data center coming online very soon, as a matter of fact. And then Georgia is a very lucrative and, for economic growth as a state. And we've seen industrial customers, especially manufacturers, come to our state, electric batteries, electric cars. So those industrial customers can range up to 500 megawatts. So we went up to our PSC late last year, and early this year in springtime, the IRP update was approved. Between the time we filed in October to this year, when the IRP was approved, we signed 2,600 megawatts more signed. It's not in queue. It's not being studied. This is signed. This is a load that's coming. They signed a contract with us. That is just astronomical growth. We used to be happy when we got a 20 megawatt customer on our system. Like, oh wow, that's huge, right? As a 20 megawatt customer, I mean, that's going to be the revenues. Well, now that just seems like way distant in the past, and we're talking hundreds and sometimes thousands of megawatts of load, and just the sheer magnitude is incredible. Nothing that we've seen before. So just another way to look at our picture in the 2022 filing, our load forecast, right? We told our PSC we see about 400 megawatts between 24 and 31. 400 megawatts. That's our load growth. Well, we went back for an update, and guess what we asked? Our queue is, we're now predicting 6,600 megawatts for the same time period, 17 times more. Yep, that's what we're asking. Because that's how fast and how strong this load came at us, about 43% increase in just what we filed in a year and a half. So it's just that this picture is basically what we are actually working on and working with. It's an interesting time to be in the electric utility and the energy industry, to say the least. I started when the AC load, the 2006 peak was huge, right? And now we're looking at this peak, and that is nothing. So this is a very exciting time to be in this industry. So just quickly, what came out of our IRP update early this year in spring. So we asked for about 3,300 megawatts of capacity that came as a mix, basically PPAs, energy storage. We have some peaker units that we are going to build, and then DER programs, so customer-based programs. Our load forecast was approved, and I'm going to touch on that a little bit. So our load forecast is also a very much a calculated forecast, very robust. Lot of customer engagement comes when we do our forecasting, and our economic development team is at the forefront in order to help us to ensure that this matches our forecast and it materializes. But I'll go over that in a little bit. So our load forecast, as we had calculated and approved, was approved by the PSC. Transmission, approved is not the right word here, but transmission, with the peaker units, we need a delivery, right? We need a transmission delivery. Aging infrastructure, how do we get this generation on our system to feed this load? So we asked for transmission to go with our peakers. And then in addition, we got approved to do some solar and battery pilot programs as well. So very constructive outcome of our IRP. Our PSC knew what we are dealing with, that we are here for an updated IRP filing for a reason, is because these large loads are not going to stop. They are going to continue coming. So really good outcome. So touch a little bit about the electric, the sales forecast. So how do we see basically the journey of the load really materializing, and what do we really include in our forecast, and especially our sales forecast? Because, when we talk about this, we're all technical folks. We talk about how do we technically feasibly integrate these loads. For us, a large corporation, there's also the consideration for sales and revenue. And how do you really level set those expectations when it comes to revenue? What is truly going to, bring us the shareholder value as well? So this is kind of just the layout of how we determine early stages, the selection of electricity provider. As I mentioned, Georgia offers choice to our customers. So our sales team does engage with our customers to bring them into Georgia Power and choose Georgia Power as our customer. So that is a very involved, very customer-focused, engaged process. And once they select Southern Company and Georgia Power as a utility, we have those detailed conversations and we collaborate with our customers, and then ultimately figure out what is our materialization rate for these customers. One of the things I do want to talk about a little bit is as we're doing this in terms of our sales and load forecast, we're continuously improving and changing our rules and regs to ensure that these large loads, when they say they're going to ramp to a certain rate, that they adhere to the ramp, they don't exceed the ramp. Take or pay mechanisms, 100% local costs are paid up front. Things like that we now are very cognizant, and we're actively working towards either changing and making sure that we're engaged with our customers in those rate mechanisms as well. So a lot of those conversations are ongoing and, as we speak right now. So a little bit of capacity needs as we go down. In fact, next year, we're going to file for our regular cycle IRP again, and also our rate case. And, what do we see in terms of our capacity needs? And, just looking at the future, 2032, just what we might anticipate is significantly higher than what we had anticipated in 22. Just being able to serve and meet the load that's coming our way. And when I say load and, geographically, just think about Metro Atlanta. That's where the load is going. A lot of these are cloud-based, so there is good telecommunication infrastructure in Metro Atlanta. As Julieta mentioned, the AI and the inferencing load could be located elsewhere. What we have seen is they tend to be in the same cluster, even though they don't need that robust infrastructure, but they tend to stay in that cluster. So Metro Atlanta is already congested, and now we have more coming that way. So it's it's basically, I relate that to the traffic in Atlanta. The traffic is already bad. I think the transmission congestion is just as bad as the traffic is going to get there. And quickly, I'll just touch a little bit on our system planning, how we do transmission in Georgia. As I mentioned, our market structure being vertically integrated, we are able to see from generation all the way down to the customer level. That gives us huge flexibility in order to see what the load needs are, what the transmission needs are, and how can we help the customer as well with our customer-based program. We also have the integrated transmission system in Georgia with 4 partners, but Georgia Power is the only federally and state jurisdiction company. So we jointly plan that system, jointly plan our transmission system. That's an art in itself. So we may not be in the ISO RTO market, but we also have our ITS partners that we jointly plan with. Along with that, we plan periodically with our regional transmission partners. So Florida, Alabama, South Carolina, Tennessee, we have a strong framework for that. Like I mentioned, we have a constructive framework with our PSC, which allows us to build transmission efficiently and quickly. Now, we also face the same challenges as industry in terms of supply chain, in terms of equipment availability, as well as resources to build this massive infrastructure that we are embarking on. So I'll end here, and I'm going to turn it over to Harish, and then we'll do questions later.
Thanks, Pooja. So good afternoon, everyone. So my portion of the talk today, I'll be focusing mainly on the interconnection and integration issues with the large loads, specifically focusing on large data centers. Okay. So when we talk about these large data centers, the considerations that we have are mainly falling into power quality bucket and the system stability bucket. And Ahmed here, and I have listed these here, and Ahmed already touched on these. And I'll be talking about these as well. And so it will be reiterating to some extent, but I'll be adding some, hopefully some extra flavor to these. So before I go into these individually, I just want to give you a high level overview of what a data center layout looks like. So data center means, of course, there will be, stacks and stacks of these racks of, servers, right? So they will be fed by these power factor corrected supplies, and there'll be UPS systems to help them ride through momentary voltages, momentary voltage sags. So all of these servers, right? You can aggregate them, and we can call them what they call IT load component. Okay. And then these servers will heat up, of course, right? So they need to keep them cool down. So there will be a lot of chillers and air conditioning. So you can expect a lot of motors and drives. So all this can be then further, aggregated into what they call cooling load. Okay. And then there will be some other miscellaneous load. So when we know that a data center is going to get connected to our system, what we do is we want to understand more about that. So what we have is that we have developed a questionnaire, and we used NERC data center information collection form as a starting point. And we sent this questionnaire out to these data center developers or customers. So we are looking for information like, of course, what's the total rated load, right? Megawatt. And like we just heard, it could range in hundreds of megawatts, could even exceed gigawatt. The other piece here is power factor. So this is very important because we are used to serving lagging power factor load. And now what we are learning here is that these data centers, they can be leading. So planning for a 0.95 lag power factor, 1 gigawatt load versus planning for a 0.95 lead 1 gigawatt power factor load, it's a very different beast. So it can make a difference between whether you would want to put a shunt capacitor banks or a shunt reactor bank, for example. So we get that information, and then we are looking for, okay, if it's a 1 gigawatt load, what percentage of that would be IT load? What percentage of that would be a cooling load? And it's important because I know Ahmed already touched on these IT equipment specifically, it's very, very sensitive to voltages and even frequencies. So if there is a system disturbance nearby and your system voltage drops, you can expect this IT load specifically to switch over to this local emergency backup generation, which tends to be diesel generation. But from a system perspective, it's like you lost that load, right? So it becomes super critical. And final piece here, it's related to more newer AI type data centers, because the traditional data centers like your cloud-based services and all, the load profile used to be like a flat line. But when we are talking about this AI-based data centers, which I'm talking about OpenAI and where they are training these large language models, it's no longer a straight line. It can be varying up and down with a very high frequency. So we are looking for that information, and you need this information early in the game, because once you have this information, then you can do certain analysis. So I'll start with power quality. And if you talk power quality, the first thing that comes to mind is harmonics. So remember I mentioned these are power factor corrected supplies, and there's a lot of drives. That means you have a lot of harmonic sources there. So what these facilities will do is they will make sure that they have harmonic mitigation measures in place, like filter banks and of that nature, so that the net harmonic injection into the utility system is limited. So what at Southern Company we have is what we call a power quality policy. And this power quality policy applies to loads and even IBRs. But of course, data centers, they fall in the load category. So for example, I'm showing a table here. It shows how much harmonic current at individual harmonics can an industrial load inject when it is connected to a transmission system. Okay. So what we are doing is we are asking for that information upfront, like what the expected harmonic spectrum is. Then what you can do is you can build a computer model. It can be EMT I'm showing here, but for harmonics, it could be a frequency domain. But once you have that model and you have the current harmonic spectrum information, then you need to know what your existing background harmonics is. Then it is possible to estimate what the harmonics would be when the facility starts operating. So those type of analysis can be done. And the critical piece here moving forward would be the monitoring, because how do you ensure that these facilities will actually meet our power quality policy? So we need to have something like this. I've shown here a power quality meter get connected to the point of common coupling. And we have been doing this for a long time for existing large loads like electric arc furnaces. We do it for IBRs all the time. So there is nothing new here. It's just extending the same philosophy and practices to these large data centers. So moving on, still sticking to power quality, but again, going back to those AI-based data centers, and we talked about how the load is not constant and it can go up and down. So that means now these large loads can become a source of voltage fluctuations, right? So once again, if you know the load profile, so that's the key. If you know the load profile, you can replicate that into the EMT model, and you can estimate what the fluctuation would look like I've shown here, right? And you can see this load profile was very cyclic and repetitive. So once you know those voltage fluctuations, you can go ahead and estimate for flicker, the index that's commonly used is PST. So you can actually compute that. So in this case, I'm showing here, we computed at 1.04. So going back to our power quality policy, in addition to harmonics, we have limits for flicker. So for us, for a transmission system, the limit is 0.8. So our analysis shows it's exceeding the limit. So what do? So we take these analysis results and share with the customer. Now this data center customer can actually do things within the facility. They can stagger their operation, and they can actually change the magnitude and frequency of these active power variations, and even the wave shape. Instead of for example, a step change, it can be a ramp change. Things of that nature they can do, and this flicker, for example, could be brought down within the acceptable levels. But if none of those measures help, then of course they have to invest in this multi-million-dollar solution like a StatCom, and I'm talking about industrial StatComs. This would be very similar to what an electric arc furnace customer would have, for example. Okay, so now we can talk a little bit about stability analysis. So we do have concerns that these large data centers, they will have, or they can have, adverse impact on stability. I'm talking about voltage recovery, rotor angle stability of nearby units. Because what we have learned is that these data centers, they would behave like a constant power load. And traditionally, constant power load doesn't help you in peak load scenarios because it doesn't help with the voltage recovery that much. But remember, I talked about how how they can switch over to backup generation. So that piece is actually going to be helpful because it's like a load shedding scheme here, right? But if you are talking about low load scenarios, right, your voltages are already high, and say you are losing 1 gigawatt, 2 gigawatt of load suddenly, you can expect even higher voltages, right? You can even have these frequency events. So you really need to study all these scenarios. It has to be a very comprehensive analysis. But the key is the modeling. You really need to have an accurate dynamic model of these data centers. You just can't use a simplified models like you could with some of the other loads. So I've listed some examples here. If you're using PSAC, you need to use composite complex load models. So that's why you need to know all that, right? How much percentage is IT load? How much percentage is motor load? Because you need to model these individually. And definitely the switchover piece becomes very critical. So when we do this analysis, and if we see that there's going to be an issue, you can do some things. You can go in for faster breakers, for example. But if even that doesn't help, then of course, you can go with something like a StatCom, and this is a utility StatCom I'm talking about, not the industrial that we talked about for Flickr. So you're seeing a theme here. There are issues and there are solutions, but you need to do your analysis. Continuing with stability, now this forced oscillations. Now this becomes an issue again with the AI type data centers that I talked about. Remember I talked about how the load can be fluctuating? And it's especially problematic if that load variation is cyclic. And seems like that can be the case here, that it's going to be cyclic means it repeats, say, every few seconds. And it's going to be like 24/7 operation. So this frequency injection, this signal, right? This low frequency injection signal is going to be there all the time. So now you need to be careful that this frequency doesn't match any of the natural modes. So if there are any nearby units, they have these torsional modes. So you need to stay away from those torsional modes. Your local area modes, your sub-regional, and the worst case, the inter-area modes. I say worst case because inter-area modes, the lower the frequency, remember, the further away it travels. So here, there is a potential that one load can have these oscillations that can be felt over the entire Eastern interconnect. Obviously, we don't want to get into that situations. So again, there are solutions to it. The easy one would be, again, once you analyze and you see that, yeah, there is a chance of these signals, low frequency signals to be injected, they can do some things at the low voltage level and smooth out those active power variations. The worst case, there are some new novel technologies being developed, but I'm showing here is this is called eStatCom. It's a special type of a StatCom. It's not your normal StatCom. It has an ultra capacitor, for example, attached to it. And instead of dynamic reactive power compensation, this StatCom does the active power compensation. So what it does is if you have active power variations coming from this data center, this will compensate for those variations. And it becomes like the goal here is to make it a straight line from the system perspective. But again, this is going to be a costly solution, but that may be the last, resort. So once again, I'll go back to this piece of monitoring. So like power quality I talked about, there needs need for adequate monitoring, the same thing here. So even though you do all the analysis, you still need to make sure that these data centers don't end up injecting any problematic signals and introduce forced oscillations. So we are looking at things like PMUs that we would be connecting wherever these data centers are getting connected, and also looking at various tools that are out there to be able to detect the oscillations and even identify the source of these oscillations. Because in very near future, we looked at how many data centers we are expecting. There's a chance that there will be a lot of them clustered at one location. So it becomes very critical to have adequate monitoring there to identify where the potential oscillations could be coming from. So if I have to summarize, like I said, amongst other concerns, I didn't touch on some of the other concerns like ramping and having adequate frequency reserve, but definitely we have a lot of power quality and stability concerns, and analysis is really needed. So if you know data center is coming, it's a good idea to commission a study, and these studies have to be done early. So it's even important that you reach out to the developers and the data center customers really early and start asking right questions. And they'll give you the information, take that, do the analysis, and then immediately share the findings with them. Because like I said, they may be able to do certain things which will avoid the need for costly, painful solutions down the line. So what we are doing is we are developing all these study processes that I talked about. We are working on technical requirements, things like write-through capability, or what kind of power factor, maybe limitations on power factor, things of that nature. And then operation protocols, of course, for ensuring smooth interconnection and integration of these large loads. And once again, I'll reiterate the final piece, monitoring. It's very critical to have adequate monitoring there, both to pre-commissioning and post-commissioning monitoring. So just to make sure that these loads will really behave like we are expecting them to be, and they meet all the requirements that are in there. I think that's all I have. Thank you.